Alrighty, in this video we're going to be doing some practice problems involving inscribed angles. So I have 3 examples total, and all of them should in some extent use the theorems we talked about in part 1 of this series. And it's also going to touch upon some other theorems that might be helpful that we learned earlier in this unit. So for my example 1, we have a circle and we have multiple inscribed angles. It wants me to use some theorems involving inscribed angles to find the value of A and B. So I'm going to just focus on one at a time. So I'm going to try and find A as of right now. And so A is attached to angle T. So something I want to note is just that the measure of angle T equals 5A degrees. So looking at measure of angle T, my first go-to for any theorem involving inscribed angles is always going to be the inscribed angle theorem itself, because it's very easy to use and it's very easy to spot. So what I'm going to do is just find that relationship first between the inscribed angle and its intercepted arc. So I can tell that angle T intercepts this circle at points Q and S. So this whole entire arc right here is the arc that's corresponding to angle T. So the inscribed angle theorem tells me that the measure of angle T is going to be 1/2 the measure of arc QRS. And I included R in here because I want to make it clear that I'm talking about the right half of this arc and not the other arc here, QTS. If I know the value of the measure of arc QRS, then I should be able to find A with no problem. Now I have a chunk of that, I have RS, but I don't have QR. So what I want to do is use the other pieces of information I have here to find QR, because I actually do have enough to find this remaining arc. Now I know that all arcs sum up to 360 degrees on a circle, and I have all of the other portions of the circle accounted for. So what I can do is take all of 360 to find the measure of arc QR and subtract off what I don't want. So what I'm going to do is subtract off 112, 120, and 64, because subtracting off the measure of those arcs will get me just QR left over. So I'm going to take 360 minus 112 minus 120 minus 64, which will get me 64. So now I can go ahead and label arc QR as 64 degrees. And now I can add together the measure of arc QR plus the measure of arc RS to find this whole arc I'm looking for, QRS. Because we know if we have adjacent arcs, then we can add their measurements together to find the whole thing. So measure of arc QR gave me 64 degrees, and the measure of RS was 112. So adding those together, I get 176 degrees total. So what I'm going to do is just mark that down here so that I don't forget. So measure of arc QRS equals 176, and now I'm going to do some erasing. So now that I have the measurement of the arc that I needed, I can go ahead and plug right in. So since I'm trying to find the measure of angle T, because T is going to bring me back to here where I can find A, which is the point of my problem. So the measure of angle T equals 1/2 of, I said that QRS was 176, and taking 1/2 times 176, I get 88 degrees. So now to finish off this problem, since I have the measurement of angle T, I can plug that back in for my first equation here. So the measurement of angle T is 88 degrees, and I can set that equal to 5A degrees. Now I have degree measurements here, but really we're just trying to solve the equation 88 equals 5A at this point. So now I can finish off and solve for A by dividing both sides by 5, since I have multiplication. So on the right side, 5 over 5 is going to cancel, and I just have A, and then 88 over 5 is about 17.6. So A does not end up being a very pretty number, but I might have some examples here and there where I have some decimals going on, so that's okay. Now that I found the value of A, I'm going to go ahead and try to find the value of B, which is corresponding to angle S. So what I'm going to do is again use the inscribed angle theorem to find B. And I already established from before that QR was 64 degrees. So that piece of information is not changing, so I can just keep it and copy it down. So what I want to do is find the arc that is intercepting angle S, and it looks like that arc is arc TR. So I'm going to go ahead and make my relationship between my intercepted arc and the inscribed angle. So the inscribed angle theorem tells me that the measure of angle S is 1/2 the measurement of the intercepted arc TQR. And again, I'm using the point Q here to specify I'm talking about the minor arc here and not the major arc. From here, I actually have all the information I need. What I can do is if I want to find the measurement of arc TQR, I want to add together the pieces I do have, which are the measurements of arc TQ and the measurements of arc QR. So doing some substitution here, measurement of TQ was 64 degrees and QR was also 64 degrees. So adding together, I get 128 degrees. So now to find the measurement of angle S, I can take 1/2 and measurement of TQR was 128. So I'm going to do some substitution, and 1/2 of 128 is going to get me 64 degrees. Now something interesting here is that because I have that this arc measurement is made up of 64 degrees twice, whenever I add them together and then divide by 2, I'm essentially just undoing the addition that I did up here. I get essentially 1/2 of that arc. So that's just something interesting that occurs with this particular problem, but it won't occur all the time. So now I'm going to go ahead and mark down the measurement of angle S before I do any erasing. So the measurement of angle S equals 64 degrees. So now that I have the measurement of angle S, I can go back to my original question, which is what was the value of B? So I can say that the measurement of angle S equals 6B degrees. And I already found that the measurement of S was 64. So really what I'm trying to do is solve the equation 64 equals 6B. So similarly to the first part of this problem, I could just divide by 6 on both sides to isolate B. So on the right, 6 over 6 is just 1, so I'm left with B. And 64 divided by 6 is about 21.3 degrees. Now, if you plug this into a calculator, you'll get about 21.3 repeating, but I just rounded to the nearest tenth here. All right, moving on to example 2. I have this circle X, and it wants me to find the measure of BCD. So I'm going to highlight that angle so we know what we're trying to find. Now, what's interesting about this problem is that I have 1/2 of BCD, but I need to find the other part here. So what I'm really trying to do before I do anything else is answer the question, what is the measure of angle ECD? Because once I'm able to find ECD, what I can actually do is add the measurements together. Because I know that the measurement of angle BCD equals the measurement of BCE plus the measurement of angle ECD by my angle addition postulate. So I have BCE already, which is 68 degrees, but I need this chunk of information before I can go any further. So I'm going to go off to the side and find this first. So if I look at ECD in more detail, I can see that it's an inscribed angle because its vertex is lying on the circle and the other 2 points intersect the circle on the opposite side. So what I want to do is use the inscribed angle theorem again here. And so if I look at that, what I have is 1/2 the measurement of the intercepted arc ED equals the measurement of angle ECD. So if I want to find the measurement of angle ECD, all I need to find is the measurement of angle ED. So what I want to do is look at the surrounding arcs that I have and see if I can figure out anything about ED using that information. So one thing that is very helpful here is that I have a diameter right here. And so my points E and C are lying on this diameter. So if I look at the arc that is corresponding to EC, which in this case would be arc EDC, I know that arc EDC is a semicircle, so that means the measurement of this arc has to be 180 degrees. So looking at just this half of the circle, I can see that the measurement of arc EDC is actually made up of measurement of arc ED and the measurement of arc DC. So putting all this information together, I know that if I add together arc ED plus arc DC, I'll get 180 degrees. And I already know one piece of information about that. I know that DC is 118. So using the 2 pieces of info I have, I can go ahead and find the measurement of arc ED by subtracting 118 from both sides. So subtracting 118 from both sides, I get that the measurement of arc ED, on the left, my 118s are going to cancel. And on the right, 180 minus 118 is 62 degrees. So going back up here, I'm going to mark arc ED as 62 degrees. And so going back to the original question I was trying to answer, now that I have the measurement of arc ED, I can do some substitution and I can get ECD. All right, so doing some substitution, I have 1/2 the measurement of ED was 62 equals the measurement of angle ECD. And so 1/2 times 62 is going to get me 31 degrees for the measurement of angle ECD. So right here, I get 31 degrees. Now, we've gone through multiple steps to get here, but we don't want to forget the original question we're trying to answer, which is what is the measurement of angle BCD? All of those extra steps we took were to get ECD, which I found was 31 degrees. But now I want to add that to BCE to answer my question. And it looks like 68 degrees plus 31 degrees gets me 99 degrees for my answer. All right, so I have one final example I want to go through. And what we're trying to do is find the measure of each minor arc formed by a regular hexagon inscribed in a circle. Inscribed means that every single vertex of the hexagon is on the point of this circle. Let's just call it circle K. And a big key aspect to this problem that's going to help us a lot is that we have a regular hexagon. Now, by definition, a regular hexagon means that all of the sides are congruent and all of the angles are congruent. So I'm going to make some little tick marks on my diagram to make sure that I don't forget that. And then in a different color, I'm going to mark all of the angles as congruent. Now, there are multiple ways to solve this problem, but I'm going to show the most efficient one so that we can see how some past theorems actually end up playing into these problems. What I want to do is find the measure of each minor arc. So looking at this diagram, I already know right off the bat that all of my minor arcs are actually going to be the same measurement. Now, I know that because say I'm looking at just this minor arc right here, and then maybe I look at another minor arc over here. I won't mark every single one, but what we'll notice is that the chord that is intercepting these arcs are all the same length. So we had a theorem in the very beginning of this unit in which if we had two chords that were the same exact length, like we do here, let's label these points A, B, and C. So I know that AB is congruent to BC. If we were given this piece of information, we knew then that naturally it follows that the measurement of arc AB is congruent to the measurement of arc BC. So if I take this logic and apply it all around my circle, all of these arcs are going to be the same measurement. So what I'm going to do is actually mark all of these as some variable x, because I'm trying to solve for x here. X is the measurement of all of my minor arcs, so I'm going to label it as something to make my life a little easier. I can use inscribed angles here if I wanted to, but there's actually a bit of a shorter way to do that using some past theorems. So when I look at each of these arcs, I know that none of the minor arcs are going to intercept one another or overlap. I actually have that they're adjacent. So they all share points, but there's no overlap and there's no gaps. So I know that all of these arcs are going to equal 360 degrees if I were to add them together. What I can do is add the measurement of arc AB plus the measurement of arc BC and so on until I get all of my arcs. And I would get 360 degrees. Now, I don't want to write every single arc down, and I don't have to because I know that I labeled each arc to be x. So if I count up all my x's here, I have 1, 2, 3, 4, 5, 6 x's total. So I know that I have x degrees plus x degrees plus x degrees, and I have that 6 times. And I have that that's equal to 360. Now I had 6 because I'm adding together 6 x's. So instead of writing 6 x's all in a row, I just added this little dot in here and I know that I'm adding them together 6 times. Now we also know that repeated addition is the same as multiplication. So really what I'm doing is taking x degrees 6 times. So I have 6 times x equals 360 degrees. So now I took all of that information and boiled it down into one equation, 6x equals 360. So now what I can do is simply solve for x and I'll actually have my answer. So to solve for x, I want to divide both sides by 6. So on the left, 6 over 6 cancels and I have x, and 360 over 6 is 60 degrees. So now going back to what the original question was asking me, I have that x equals 60 degrees and I labeled x as any of these minor arcs. And that's exactly what this question was asking for. So to answer the question in full, I have that the measure of each minor arc formed by a regular hexagon inscribed in a circle is 60 degrees.